So now we're going to talk about the Floyd Warshall algorithm, which is an algorithm for finding shortest path between all pairs. So if we want to find the shortest path between all pairs, we can use Dijkstra algorithm as well. So Dijkstra algorithm finds the shortest path from a single source. So we just need to repeat the algorithm n times, where n is the number of nodes. So we start with every node, treating it as a source. We run Dijkstra, we get the distance, and then we can start with the second node, and so on. So Dijkstra, in our implementation, it has a complexity of E log V, because we may have the number of Q operations is linear in the number of edges, and each Q operation may be log. So log E, and it's the same as log V except for a constant. So running it n time has complexity NE log V. Floyd Warshall, on the other hand, has a complexity of n cube. So it's not complexity-wise. It's I guess yeah. So it's similar to Dijkstra, depending on how many edges a graph has. If the graph is really dense, where E is close to n square, so almost every pair there's an edge, then Floyd Warshall's complexity is lower because it doesn't have the log factor. On the other hand, if the graph is sparse, then, for example, E may be on the same order as N. In that case, then actually using Dijkstra is better to find all shortest distance between all pairs. So there's at least one user code problem where you cannot use Floyd Warshall, but you actually can use Dijkstra. That's the case when I think it's kind of when you have an implicit graph. For example, you can, from every cell, you can move to 4 adjacent cells. So then the number of edges is 4 times the number of nodes. So then using Dijkstra in that case will give you n square log n complexity, and Floyd Warshall will have n cube. So I guess here instead of v it should be n. So Floyd Warshall has the advantage that the code is really easy to write. It's literally 4 lines of code. The main body is just 4 lines, and the constant is also very small because the code is very simple. So it can scale up to n is 400 or even 500. So if you see a graph with nodes in that range, then there is a possibility that the intended solution uses Floyd Warshall. So the algorithm uses a dynamic programming. So we're going to look at the pseudo code on the next slide, and I'm going to explain. And the algorithm is correct even when there are negative edge weights. So that's the Dijkstra doesn't will not be able. So Dijkstra may not be correct when the sum of the edge weights are negative. However, Floyd Warshall cannot detect negative cycles. So essentially, if you have a negative cycle in a graph, then the concept of shortest distance becomes meaningless, because once you get on the cycle, you can go around, and the distance will just be smaller and smaller. So when there is a negative cycle, there isn't such a thing as a shortest distance. So typically, you will just detect that and then sort of report that. So Floyd Warshall cannot detect it. So when there isn't a negative cycle, but there are negative weights, Floyd Warshall remains correct. To deal with negative cycle, we have to use the Bellman-Ford algorithm. So this is a pseudocode for the Floyd Warshall algorithm. So the triple loop. Yeah. So there are initialization. So the distance, we want to initialize a distance array for between every pair of nodes. So every node to itself has distance 0, and for any edge UV, we assign distance to be the weight. So other pairs are initially assigned infinity. So after initialization, it's just this triple loop. so K will range from 1 to number of to the number of nodes. So essentially, what this outer loop can be viewed as, we consider the shortest distance between any pair of nodes I and j if we're only allowed to use nodes between 1 and k as the intermediate nodes. So we're not allowed to go through any nodes which is higher than k. So initially, every node to itself distance is 0, and these are all direct edges. So initially, the value is we're not allowed to use any node as the intermediary, and what's the shortest distance. So that is the initial value. So then we look at, well, now we're allowing to use node 1 as an intermediary and see what shortest distance does it have. So then basically we'll look at, well, to calculate the distance from I to j, we look at what is the shortest distance from I to 1, and then the shortest distance from 1 to j, and then we add it up. If that is smaller than the current shortest distance, then we will update the current shortest distance. So because we don't consider the possibility of negative cycle, so the shortest distance from I to node 1 should not involve using 1 again. So because then it's a cycle. So then the distance when k equals 1, we're not using any other intermediate node from I to 1, and not any other intermediate node from 1 to j. And then we combine those two sort of shorter paths. If it gives us a shorter path, then we will use that to update the distance ij. So after this loop, we computed all the shortest distance between I and j when using 1 as the intermediate node, when 1 is being allowed to use as intermediate node. So we don't have to use 1, but 1 is allowed. So then when k equals 2, we are computing the shortest distance when nodes 1 and 2 are used as the shortest path, can be used as the intermediary. So if 2 is used on the path, then the shortest distance from I to 2 must not use 2 and only use 1. And similarly, the shortest path from 2 to j should not use any other node. So this is sort of the dynamic programming interpretation of Floyd Warshall, which is we are gradually computing the shortest distance between any pair of nodes when we are only allowed to use a prefix of all the possible nodes. So starting from not allowing any intermediary until we go all the way to all the nodes are allowed. So that's the Floyd Warshall algorithm.